I'm going to be working the homework set for 2.7, which is related rates. I've got about 40 minutes, so let's see how many of these I can get through. Problem number 1. If V is the volume of a cube with the edge of length x, and the cube expands as time passes, find dv dt in terms of dx dt. So we have a cube, three-dimensional, all sides are the same length. It's telling us that the cube expands as time passes. The volume is V, and it asks us to find dv dt. So I want to find dv dt, and I want to find that in terms of dx dt, which means that this should equal to something and it should have dx dt in it. So what we need to do is come up with a relationship between the variable v. I'm going to put dx dt here just so that we know that's going to be in our equation. We need to somehow find a way to relate v and x together. And v is the volume of the cube, so there's a formula for the volume. Volume is length times width times height. But since all the length, width, and height are the same, it's just volume is x cubed. And now what I can do with this equation is differentiate it with respect to time, because time is my independent variable. And so the derivative of the left side with respect to t must equal the derivative of the right side with respect to t. And since neither one of these variables match up with t, right, neither one of these have t in it, the derivatives are just going to be, well, derivative of v with respect to t is dv dt. And then over here we have a derivative of something that's being cubed, so I have to use chain rule. So 3x squared, but then times the derivative of what was here with respect to t, which is just dx dt. And as you can see, I've come up with a relationship where I've expressed dv dt in terms of dx dt. I also have it in terms of x, but all that was required that I get it at least in terms of dx dt. So I am done. Now the next problem says, if A is the area of a circle with radius r, and the circle expands as time passes, find dA dt in terms of dr dt. So we have a circle, and what's happening is that it's expanding. So imagine you have a circle, here's the radius, it's getting larger and larger as time goes on, and I want to find a way of relating dA dt, okay, in terms of dr dt. So very similar to the previous problem. Well, I need to find a way of relating area and radius, but that's clear because the area of a circle is pi r squared. Remember, pi here is a constant. And now if I differentiate both sides of this with respect to time again, then the derivative of a with respect to t is just dA dt, which is good because that's what we're trying to figure out. And equals, now pi is a constant, time's a function. The pi is just going to come along for the ride. And then I need to multiply that times the derivative of r squared. Now r is like something squared. So the derivative of something squared is 2 times the r to the first power. But then chain rule says times the derivative of what was down here with respect to time. So dr dt. And you can see here, I can move the 2 in front of the pi. I get dA dt equals 2 pi r dr dt. So I have expressed the area, the change in area, dA dt, I've expressed it in terms of dr dt. Notice we also would need to know what r is, but the problem just asks us to express that with this in it. So I've got it. That's the answer. That's part A. Part B says, suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing? So this is related to this problem, the thing we just did, but I'm going to start this kind of from the beginning. all right? So we have oil that's being spilled. So here I'll demonstrate my artistic abilities here. This is a 18-wheeler truck, whatever. And it's ruptured here, and there's oil spilling on the ground, and it's creating a circular oil spill, and that circular oil spill is spreading out as time goes on. That's perfect, isn't it? And now what I need to do is try and figure out, it tells us if the radius of this circular oil spill is increasing at 1 meter per second, how fast is the area increasing when the radius is 30 meters. So like I said in class, you're going to want to draw two pictures. You're going to have a general picture, the general situation. You're going to have a problem, an instant picture, which is going to be the instant in time. So in general, we have a circle. We have a radius that's not fixed, it's growing. So in general, this is our picture. And we're talking about area here. So we know that we're somehow going to be able to find the area of a general circle. At the instant in time, they want to know how fast is the area increasing when the radius is 30 meters. So when this is 30 meters, when R is 30 meters, they want to know some information. So I'm given some stuff. I'm given that the radius changes with respect to time, right? I'm given the rate at which the radius is increasing. They tell me it is 1 meter per second, and I'll read that. If the radius of the oil spill increases at a constant rate of 1 meter per second. So the radius increases at a constant rate. Rate means derivative. So I know dRdt is 1 meter per second. They want us to find, right, this is what I'm given, what I want to know, or I should say, what I want, is to know how fast the area is increasing with respect to time. And I want to know that exactly at the moment that the radius is 30 meters. Okay, so I have generally the picture is that it's growing. But at an instant in time, at 30 meters, I want to know how fast at that instant the area was increasing. And I know that the radius is increasing at 1 meter per second. So got everything here. Now what I need is the equation. I need an equation that relates these two variables together. I need to somehow try and relate A with R. All right, so what formula that goes with the circle would relate the area to the radius? Well, we just did that. Area is pi r squared. And so we differentiate with respect to time, which is what we did in part A. I won't redo it. Make sure I'm on camera here. I am, okay. So that's our formula. And now what we do is we just check dAdt is what I'm solving for, so that's good. Do I know the radius at the instant in time? Yes, the radius is going to be 30. And do I know dRdt? Yes, it is 1 meter per second. So I should be able to plug in R, dRdt, and that'll give me dAdt. Just remember that when you write your equation, you do not put any constants in here unless that variable is fixed the entire time. And in this case, the oil spill's changing, right? The radius is changing. So I only plug in the 30 after I have taken the derivative. All right, so derivative first, then here, and just going to plug in. So dAdt will be equal to 2 pi, the radius is 30, the dRdt is 1, so this gives me 60 pi. Now 60 pi what? I could have put all the units in there, like I could have put 30 meters and then 1 meter per second and canceled meters, but I like to just go back and look at your answer here and think about what it should be. Area is measured in square units, so it's either square feet, square meters, square miles. So I know that my answer is going to be in square units, and then I just ask myself, what was my unit of measure? Meters, right? So I'm going to have meters squared per because this is division, time unit. The time unit here was seconds. So meters squared per second. I said earlier the meters would cancel. I'm sorry, the meters would not cancel. If I plugged them in here, they would actually get squared. So that's it. 60 pi meters squared per second is the rate at which the area is changing at the instant that the radius is 30 meters. Okay. 3. Each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? So we have a square. All right, let me draw a general picture. We have a square. Because it's a square, I can call that x and call that x. And what I know is the square is growing. That means that we could say this x is getting bigger, like so that point's moving this way. At the same time, that point's moving up. And so as this goes over and this goes up, the square gets bigger and bigger and bigger. We'll just say that this point just stays fixed. So you've got this growing square. Now, at the instant in time that they want to talk about here, my square has actually reached a point at which the area of the square, okay, so at the instant in time, the area of the square is 16 centimeters squared. All right? I am given the rate at which each of the sides is increasing. So it says each side of the square is increasing at a rate means derivative, of 6 centimeters per second. So I'm given how fast each of these sides are growing. And since I've labeled them x, I'm going to be able to say dx dt, the rate at which the x sides are changing with respect to time, is 6 centimeters per second. Just double check it was centimeters per second, yes. I'm given that. What I want is to know how fast the area is changing at exactly the moment that the area is 16. So exactly at the moment that the area of this square reaches 16, how fast was the area changing? And keep in mind that the rate at which the sides are changing is this. So I think I have everything I need to proceed. I have to figure out a formula that connects a to x, the area of that square to the length of one of its sides. And since it's a square, it's just a is x squared. And then I differentiate with respect to time. When I differentiate the left side with respect to time, I get dA dt. When I differentiate the right side, I get 2x, power rule. Then the derivative of x with respect to time, which is dx dt. And then I think about what I'm looking for. dA dt is what I want, that's good. dx dt I actually know is 6, but I also need to know what x is. And I'm not given x at the instant in time. What I'm given instead is the area. But I can figure out what x is if I know the area is 16. See, since the area is always x squared, then, and I know the area is 16, I can take the square root on both sides and get 4. And I can throw out the negative because the length of the side of the square can't be negative. Hold on just a second. Okay, sorry about that. That. All right, so where was I? Okay, so I don't have to consider x as being negative because it's the length of a side of a square. So x must be 4, and so I can go back here now and write dA dt will be equal to 2 times 4 times dx dt, which was 6. And so this should be equal to, let's see, 48 what? dA dt. So I have an area over time. Area is measured in square units. Here everything's in centimeters, so it's going to be centimeters squared per, and the time unit is seconds. So 48 centimeters squared per second is the rate at which the area is increasing at the moment that the area is 16 centimeters squared. Or you could say the rate at which the area is changing is 48 centimeters squared per second at exactly the moment that the square is a 4 by 4 square. All right. Now number 4 is similar. I'm going to leave these things here that I'm going to be using most of the time. I forgot, this was the equation. Okay, so those are kind of the things I'm going to try and do. It doesn't always work, but these are things I'm going to try and do. The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So this is similar to the problem we just did, except that it's not a square, it's a rectangle. And the rate at which the sides are growing are not the same for both sides. So in general, I have, let's see, I'll call this side, I call it L for length, I call it X, whatever I want, I'll call it X. This side is X, this side is Y, they're both growing. So this is growing, let's say that direction, this is growing that direction, we'll say that point's fixed. So this side gets longer as this side gets longer. Now at the instant in time that we're talking, the length is 20 centimeters and the width is 10 centimeters. I know from the problem that the length is increasing at 8 centimeters per second. So this length right here, right, is increasing at 8 centimeters per second. I can write that as dx dt is increasing at 8 centimeters per second. But I'm also told that the width of the rectangle, which is the y, is increasing at 3 centimeters per second. So dy dt, the change in y with respect to time, is 3 centimeters per second. What I want to know is how fast the area of the rectangle is changing. And I want to know that exactly at the moment. It says when the length is 20 and the width is 10, how fast is it growing? So I want to know how fast the area is changing with respect to time at exactly that moment when x is 20 and y is 10. So what I need now is an equation that relates the area of the rectangle to the two other variables here, x and y. Well, that's pretty straightforward. The area of that rectangle should be length times width, so x times y. And so what I need to do now is differentiate this with respect to time. The derivative of the left side with respect to time, dA dt, done, no problem. Here, we have to take derivative of this side. I'm going to go a little slower here. Times y, x times y, which means that we're going to have a product rule. So it's a derivative of the first one times the second plus the derivative of the second one times the first. So derivative of the first one with respect to time is dx dt times y times the second one, plus the derivative of the second one, dy dt, that's a terrible y, times the first one, x. And then I take a look. I'm trying to solve for dA dt. Good, I've got it. dx dt, do I know that? Yes, it's 8. Do I know y at the instant in time? Yes, it's 10. dy dt, do I know it? Yes. X? Yes. So I've got everything I need. I can solve for dA dt. I'll do it right here. dA dt is equal to dx dt, which was 8, times y, which is 10, plus dy dt, which is 3, times x, which was 20. And again, notice I'm not using my units. I'll get my units at the very end. So dA dt should be 8 times 10, it's 80 plus 60, 140, 140. And then it should be area, a measurement of area over time. Area is squared units. I'm working with centimeters, so this should be centimeters squared per, because division here, time unit here was seconds, so centimeters per second. And that's it. I wanted to show you real quick, had I instead tried, shoot, I just erased what I needed to show you. Let's say I write down this equation, okay? But I write it down with the units, just to show you how it would work. It would have been dx dt, which was 8, I'm going to write it like this, centimeters per second, so that's like per 1 second, you could say, times y. Y was 10, but 10 centimeters, so 10 centimeters over 1, and then plus dy dt, which was 3 centimeters per 1 second, right? I erased it, but it said 3 centimeters per second, and then times x, and x was 20 centimeters, so I'm going to write 20 centimeters over 1. So I just wrote them like fractions so that you can see that when you put this together, you multiply across the top here, you get 80 centimeters squared over second, 1 second, plus 60 centimeters squared over 1 second. These have the same denominator, so this becomes 140 centimeters squared over 1 second, or I can just say per second. So it's the same answer, but just different way of doing it. I think this is useful. I mean, it's not bad, but here, I guess in this class, we can always determine the unit pretty easily by just looking at these two things. All right, number what? Next. Number 5. A cylindrical tank with a radius of 5 is being filled with water at a rate of 3 cubic meters per minute. Now, when we see cubic meters, we need to be thinking volume. How fast is the height of the water increasing? So, let me try and draw a general picture. General picture, we have a tank, cylindrical tank. It has a radius of 5 meters. That's fixed the whole time. And it's being filled with water, right? So we've got water being poured in here. Here's water being poured in. And the water level is somewhere in here, and the water level is going up, right? Because the water is going in, okay? So they tell us how fast the water is going in, and I'm gonna write that down right now, what I know. I know that the volume, right, is increasing at a rate of 3 cubic meters per minute. So that is the change in volume with respect to time is 3 cubic meters every 1 minute. So when we see cubic meters per minute, that's a rate. So we know it's a derivative. And because it's cubic units, it's volume. So we have to kind of interpret that from the wording. So we know that. What we want to know is how fast the water level is rising. So the water level is actually the measurement from the bottom of the tank up, which I haven't labeled yet. And I think what I'll do is I'll label it H for height. You could have used any letter there, but that makes sense to put H. So I want to know how fast H is increasing. I want to know the rate, so it's a derivative, the rate at which H is increasing. But the thing is, it doesn't tell me in the problem when to look. Okay, it doesn't say like at a specific moment. So the instant in time for this problem, there is none, not applicable. Because if we pour water in at a constant rate, and this is a cylindrical tank, this should just come up at a constant rate also. It doesn't matter where I am on the tank, it's still going to come up at the same rate. Compare that to a problem like this, where if we had a conical tank and we had the water going in, then that would be different. It would go up faster in the beginning, and then it would slow down as time went on, as we, I'm sure, talked about in class. So we don't have this instant in time, so when we say we want dHdt, we don't have anything to say like at a particular moment. So we're just going to keep working. What I want to do now is try and come up with an equation that relates this and this. So how is the volume of a cylindrical tank related to its height? Or sorry, how is the volume of a cylinder related to its height? So I'm talking about the volume of this piece right here, not the volume of the whole tank. So what's the volume of that blue piece? Well, if you look in your book, you'll find that the volume of a cylinder is pi r squared h. That's the volume of a cylinder. In this problem though, the radius is always 5, right? That never changes ever, ever, this radius. So I can, at this point, replace this radius right here with 5 and square it and get 25. And I'm allowed to do that before I take the derivative, but only because it's constant throughout the entire problem. So that's the equation I'm going to differentiate. I'm going to differentiate with respect to time. Derivative of the left side is dv dt, which is what I am given, right? I was given this. And then over here, 25 pi is a constant, so I'm just going to write it down. And then times the derivative of h with respect to time, which is dh dt. dh dt is what I'm trying to find. So you can see here, here's what I want to know, and this is what I was given. So I should just be able to plug in 3 here. And then divide both sides by 25 pi. So dh dt should be 3 over 25 pi. And then what are my units? Well, height should be this height, and we're measuring everything in meters, so it should be meters per, and then my time measurement in this problem is minutes. So meters per minute. That's it. I'm not going to get a decimal, I'm just going to leave it. All right, let's look at number 6. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? So we have a sphere. Here's my general picture. Has a radius. That radius is increasing. That's what it says. Tells me that that radius is increasing at a certain rate. So I'm going to write that down over here. I know, or I'm sorry, I'm given. I don't know, I do this different ways sometimes, I apologize. We write down what we're given and what we want, okay? Or what we know and what we want. I'm given that the radius is increasing at a rate of 4 millimeters per second. Okay. How fast is the volume increasing? How fast is a rate? I want to know how fast, right? The volume is increasing at exactly the moment that the diameter I'll put capital D, equals 80 millimeters. So now that can help me draw my instant in time. At the instant in time I'm talking about, this sphere has a fixed radius of 80 millimeters. All right, so I'm going to try and come up with my formula now that's going to relate the volume of a sphere to its radius. The volume to its radius. So you can look it up in the book also. Its volume equals 4/3 pi r squared. That's the volume of a sphere. Wait, 4/3 pi r cubed. I don't know why I said that. 4/3 pi r cubed. And that's it. We have V and we have R in there, which is good, because we have V and we have R here. So notice I'm not going to fix my radius at anything yet. I'm going to take derivative because the radius is changing. So I take my derivative on the left, dv dt. Over here, 4/3 pi is a constant, so it's just going to come along for the ride. The derivative of something cubed is going to be 3 times that something squared, but then times the base, which is dr dt. And I can clean up, these 3's cancel. I get dv dt equals 4 pi times r squared times dr dt. And that's what I'm going to work with. dv dt is what I'm looking for. dr dt I'm given. But then I also need r. I need the radius at the instant in time. Oh, shoot. I accidentally wrote that. I'm sorry, that was diameter. Diameter straight across. Okay, let me fix that. The diameter straight across was 80. I want the radius. The radius obviously is half the diameter, so the radius is equal to 40 millimeters. So the only thing that was wrong there is my picture. So that's just one little tweak in the problem you got to pay attention to. They give you diameter, not radius. So when you come in here, you need to convert that diameter to the radius before you can plug it in. So let's plug in. If we plug in, we're looking at dv dt should be equal to 4 pi times 40 squared, not 80, times dr dt, which was 4. And if you do this, you get 25,600. And then my units will be the measurement of volume, which is whatever the unit is cubed. So it's going to be millimeters cubed, cubic millimeters, over time unit, which is seconds. And that's it. That's the rate at which the volume is increasing at exactly the moment the diameter is 80 millimeters. Number 8. These are going a little quicker than I thought. Probably too quick for you, your opinion, right? Instead, I'm probably moving a little too fast. I apologize. All right, this problem is different. All right, it says, suppose you were given an equation, 4x squared plus 9y squared equals 36. So this is a curve, all right? If we draw it, it's a curve. And part A, it says that x and y are functions of time. So as you draw the curve, right? Imagine a clock running in the background, and you have some way of drawing it, right? And they're telling you a little bit about how you're drawing it. It says, for part A, suppose that dy dt is 1/3. So the rate at which y changes is constant. It's 1/3. So the y coordinate is always changing at a certain rate as you draw it. It says for us to find dx dt at the moment that x is 2, at the moment x is 2, and y equals 2/3 root 5. Okay, that's part A. So what I need to do is somehow figure out dx dt. So I'm going to need to have some equation that has x in it, and I need to have also an equation that has y in it so I can relate those together. And the equation I'm going to use obviously is the equation that's given because I'm working on that curve. So I'm going to take that equation. See, I'm not drawing, I don't have any pictures really I need to draw here. I mean, I could draw the curve, but I don't really need it. I'm going to take the derivative of this whole thing with respect to time. So the derivative of 4x squared with respect to time will be 8x times, so I just did power rule, 2 came out, replace it with a 1, and now I take derivative of x with respect to time, which is dx dt, plus, now I take derivative of 9y squared, so the 2 pops out, we get 18y to the first power, times the derivative of y itself, right, which would be dy dt, and then equals the derivative of the right side, which is 0. And notice that in this new formula, this new equation, dx dt is in there, dy dt is in there, I know what that is, x and y are also in there, and I know what those are. So I should be able to solve for this. So I'm just going to rewrite it, 8, now x is what? 2, so 8 times 2 times dx dt, plus 18 times y, that's a weird one, 2/3 root 5, times dy dt, which was 1/3. That must equal 0. So let's try and clean this up. Let's see. This is 3 goes into here 6 times, but then 3 goes into that twice. So we should just have 4 root 5 here. And then in front of it, we should have 16 dx dt equals 0. I'm trying to solve for this, so I'll move that to this side. 16 times dx dt equals negative 4 root 5. And then divide both sides by 16. And that reduces. So you get dx dt, that's a t, sorry, equals negative root 5 over 4. And that's it. That's what dx dt is. So if you draw this curve in such a way that the y, as you draw it, the y coordinate is always changing at a rate of 1/3, and maybe it's 1/3 centimeters per second or feet per second, whatever it is, just that's the rate, 1/3. Then at the moment you get to this point, this x and y coordinate, your x coordinate must be changing, okay? The left and right must be changing at that rate, negative root 5 over 4. So you're actually going to be coming, as you're drawing it, down to the left. I mean, sorry, to the left. At that point, you're drawing to the left a little bit. All right. Part B, I think I'm going to leave part B to you because what they do is they switch it around. They give you some information about dx dt. They want to know dy dt, and they give you a different point. And then you just go through the same thing. So I'll let you enjoy that yourself. But the answer you should get on part B, oh man, I didn't finish solving it. Oh well, you can figure it out. I thought I'd finished. All right. I started doing all the problems on paper before I did the video because I was like, well, just to be sure that I make sure I get everything right. And then I got to number 8, part B, and I was like, okay, I'm done. I'm just going to go make a video. So starting now, I have not worked these out. I can't remember the last time I worked these out. So if a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. We've got a snowball. I'm going to draw you a picture of a general snowball. We don't see these in Texas. We're assuming it's spherical, okay? And since it's a sphere, it has a radius. And what's happening is as it melts, it gets smaller. So obviously if it gets smaller, that means the radius is decreasing. But as it gets smaller, the surface area decreases also, and the volume. All those things are getting smaller. But in this particular problem, they're interested in finding the rate at which the diameter decreases. So I'm going to start writing that stuff down. I want to know the rate at which the diameter decreases. So I want to know the rate at which the diameter decreases. I want to know capital D is diameter. I want to know that rate. I know it's going to get smaller, but what is the rate it does? I want to know that at exactly the moment when the diameter is 10 centimeters. And what I'm given in the problem, and I could draw my instant in time now, because at the instant in time, I know that this snowball has a diameter all the way across of 10 centimeters. That's the instant in time. But I'm given that just the way it melts, its surface area is decreasing at a rate of 1 square centimeter per minute. So the rate at which its surface area, I'm just going to put A, and not surface area, just area, and we understand it means surface area. The rate at which it's decreasing is 1 centimeter squared per minute. Now it's decreasing, so since it's decreasing, I'm going to put -1 centimeter squared per minute. Right, so let's just recap. We've got a snowball, right? We've got this snowball. It's melting, so it's getting smaller. It's getting smaller in a way that the area decreases at 1 centimeter squared per minute. I want to know at the exact moment that the diameter of the snowball is 10 centimeters, how fast is the diameter shrinking? So I need a way now to relate the diameter of a sphere, a ball, to the surface area of the ball. So we're going to have to look this formula up. The formula should be, I think it's on your first page of your formula sheets. Yes, it is. Has a sphere there. It says V is 4/3 pi r cubed, and then right below it you'll see it says A is equal to 4 pi r squared. So we know that the area of a sphere is 4 pi r squared. Now this is good, that's a good formula because it has area in it, but it doesn't have diameter. It has radius. So there's a couple of things we can do here. We can just work with that, or we can actually try and replace that r with d. And just remember that when it comes to the relationship between r and d, the diameter is twice the radius, right? So if I solve this for r, I get half the diameter is the radius. So I think that's obvious to most of us. I could take this and just go into this formula and replace that r with 1/2 d before I take a derivative. But be careful, it's being squared, so I'm going to put 1/2 d squared. And the importance of putting in parentheses is that you have to square the half. So you square 1/2, you get 1/4. You can bring that out, and it cancels out with that 4. 4 times a fourth is 1. So you're still going to have just pi here, but now the constants are kind of gone except for pi, and then you have capital D squared. And that's actually a pretty nice formula. I can differentiate that with respect to time now. So dA dt equals, the pi is going to stay, the 2 is going to pop out, so 2 pi d to the first power times chain rule, the derivative of d, capital D with respect to time, and dA dt I'm given, capital D I'm given 10, and dd dt is what I want. So I have everything I need here. So let's rewrite it. Left side becomes -1 equals 2 pi times capital D, which was 10, and then times dd dt. This is -1 equals, I'll just multiply those together, 20 pi dd dt, and then divide through by 20 pi. So I have it, -1 over 20 pi. That's a very small number. Now, what is the unit there? Well, D is the diameter, right? And the diameter of the sphere should be measured in centimeters because everything's in centimeters. So the units on this should be centimeters diameter over the unit of time, which is minutes, centimeters per minute. So as this snowball melts, the area is decreasing, the surface area is decreasing at -1 centimeter squared per minute. At the moment the snowball is 10 centimeters in diameter, the diameter is actually shrinking at a rate of -1/20 pi centimeters per minute. Awesome. 12. I think this will be my last one for right now. I always tell you all that, but it really doesn't matter to you, right? All right, this one's going to be tricky. This one's different. It's very strange. At noon, okay, at noon, I'm just going to start writing things down. At noon, ship A is 150 kilometers west of ship B. I'm going to just put B. Ship A is, okay, let me just draw this situation right here. West, so if we were to put a map here, okay, north, east, south, west, right? Then I can just start putting my ships here. And I don't even think I'm going to use the map. I'm just going to put at noon, here's what I've got. At noon, you've got ship A right here. You've got ship B right here. And the distance, it's A is west of B, so west is that direction, so this is 150 kilometers. Okay, that's the start. All right, next thing. Ship A is sailing east at 35 kilometers per hour. So this ship right here, A, is sailing east. It's going in that direction at a rate, so that's a derivative, at a rate of 35 kilometers per hour. So I'm just going to put that above here. 35 kilometers per hour. I hope that comes out on camera. Ship B is sailing north at 25 kilometers per hour. So this ship is sailing north at 25 kilometers per hour. Okay, so they're sailing at exactly noon. This one's 150 kilometers west of this. A is west of B, but A is moving this way and B is moving that way. How fast is the distance between the ships changing at 4 p.m.? All right, so let's look at what's happening at 4 p.m. That's my picture at noon. See, this is a problem where I don't really have the general picture, instant picture. It's not coming right away because it's not as a simple geometric shape, all right? It might turn into one, but just right now I'm just writing down the information, trying to make sense out of the picture, or out of the words. So let's see, at 4 p.m., that's 4 hours later, right? That's 4 hours later. What's happened is that this ship here, A, has moved how far in 4 hours? So you take this number, this is kilometers per hour. In 4 hours, it will have moved 140 kilometers. So you just take that multiplied times 4. It's 140 kilometers. Let me draw. This is where they were to start, okay? So this ship A has now sailed to here, right? It's now gone 140 kilometers, which means it's still 10 kilometers from where B started. Fix that. So A is right there now. And then B has sailed for 4 hours at 25 kilometers per hour. It's now 100 kilometers away. So B has gone up here and now is 100 kilometers away. This length right here is 100 kilometers. And that's where B is now. Okay, if that makes sense. This, if I say this was the starting point of B and this was the starting point of A, that's this point and that's this point. So in 4 hours, A has gone from here to here and B has gone from here to here. It's saying at that instant, right now at 4 p.m., find the rate, sorry, I looked at the wrong problem. How fast is the distance between the ships changing? So they want to know at that exact moment in time, how fast is that distance right there between them changing? So this one's still coming in, this one's still going up, and that purple line is changing as they move. So this is the initial situation. This is the situation at the instant in time. So I think I will label this instant. And now what I need to try and do is come up with some sort of general picture. So this is what happened after 4 hours. But what would have happened after 1 hour or 2 hours, or maybe just like H hours? How about that? At H hours, what would it have looked like? Well, we can make this a lot more complicated than it has to be, all right? What I want you to see is this picture. I'm going to erase this for right now. What I want you to see is that we have a right triangle, okay? And here's the situation. We have this base, and we have this side, and we have this hypotenuse. It's a right triangle because it was east-west, north-south. And I know that this side right here represents the length of the distance from ship A to this point. And I know that that side, I can call it anything I want. I'm going to just call this X. And I know this side right here, I can call Y. All right, great. And then let's call this right here Z, the hypotenuse. Let's call it Z. We could have called it H for hypotenuse, but all right, there we go. That's the distance, these distances. Now, what I'm given in the problem is that X is changing. And I'm given the rate at which this is shrinking, because when we start out, we're here, so X is this whole length, and then X starts to shrink, 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 shrink. So the rate at which it shrinks is the speed of the ship. And the speed of the ship A is 35 kilometers per hour. So I know that this shrinks at a rate of 35 kilometers per hour. If it were going the other direction, going away, then it would be positive. Now dy dt, dy, this was dx dt, not dx dy. I don't know why I put that. Dx dt, the rate at which x changes with respect to time is this. The rate at which y changes with respect to time is actually going to be positive, because as ship B sails, it goes this way, y gets bigger. So I use a positive number here, and it was 25 kilometers per hour. And what I want to know is the rate at which z is changing with respect to time. And when do I want to know that? I want to know that when this ship is here and this ship is here. So in terms of my triangle, this side right here is x, right? And at the moment in time, 4 p.m., that's 10, right? That's 10. So I want to know this at the moment that x is equal to 10 kilometers. See, I can't say 140, because 140 kilometers is how far it's sailed. When I get to 4 p.m., this side of the triangle is 10 kilometers. So that's why I'm using 10. And then for the y value, it's this distance, which is the 100 kilometers. So when y equals 100 kilometers. I really hope that makes sense. All right, I just need now an equation that is going to relate x, y, and z together, and that's a right triangle. We have the Pythagorean identity, a squared plus b squared is c squared, so I can write x squared plus y squared equals z squared. None of these are constant, right? As the ships move, none of those stay the same the whole time. At the instant, at 4 p.m., yes, we can talk about what they are, but not yet. We have to take derivative first. So we take derivative with respect to time of each of these. And they're all going to look very similar. We have to do chain rule. So 2x and then the derivative of x with respect to t, plus 2y and then derivative of y with respect to t, equals 2z and then dz dt. So all those derivatives we use the chain rule. Do I know what x is at the moment in time? Yes, it's 10. Do I know what dx dt is? Yes. Do I know what y is? Yes. Do I know what dy dt is? Yes. Do I know what z is? No, I don't actually. Dz dt is what I want. So the only thing I really just need to resolve is this z. Do I know what it is? Well, I can fix the moment in time right now. If I fix the moment in time, my triangle looks like this, 10, 100, and so this side I can get z, right? Because I can just use Pythagorean. So I know 10 squared plus 100 squared must equal z squared. So 100 plus 10,000 equals z squared. So 10,100 equals z squared. And I'll take the square root on my phone. (10,100) square root 100. So z is equal to, I'll put it here, z is equal to 100.498. Really close to 100. So now I just plug in. Also notice there's a 2 here, 2 here, 2 here. I could divide both sides by 2. That'll just make my computation a little bit easier. This is gone, that's gone, that's gone. And so I have 10 times 10 is x, dx dt is negative 35, plus y, which is 100, times dy dt, which is 25, equals z, which is 100.498, and then dz dt. So let me compute this. So we have negative 350. I didn't need my calculator for that. Plus 2,500 equals 100.498 times dz dt. And I put those two together and divide by this. 498 equals 21, I get a positive number, 21.39 equals dz dt. And this is measured, the units here, z is the measurement from here to here, and we're measuring lengths with kilometers. So this is 21, I'm gonna say 0.4 kilometers per, and then time unit here was hours. That's the rate at which the ships are moving relative to each other, right? The distance between them is actually increasing at a rate of 21 kilometers per hour. I'm gonna check this real quick. This is number 12. Let's see if I even have even numbers, answers in here. I don't think I do. Well, I'll check it, and if it's wrong, I'll put a note, but I'm pretty sure all the math there is good. All right, continue in a little bit.